And I met him 3 years ago at CKW, and he presented a poster about Isaac in indoor scenario at the time. And the topic was quite interesting. And since then, we keep in touch with. And he also spent 3 or 4 months, 2 years ago in my lab. So today he will talk about the title is very broad, but it accounts for 60 watts and beyond, and there are several subtopics. So take your time and please give a big hand to Dr. Yu.
So thank you, Professor Choi, for inviting me here. I'll be talking about some of the new topics that our lab has been researching. I think most of us are wireless communications technology researchers. So I will not go through the fundamental ideas of wireless communications, but just the three topics shown here, which is over-the-air computing, waveform design techniques for doubly dispersive channel, especially building on this waveform called the AFDM, Affine Frequency Division Multiplexing. Maybe you have heard of this before, but we have already built upon a lot on this AFDM waveform, presenting two new waveform based on that. And then finally, very briefly, something called the quantum accelerated optimization. So we want to use quantum computing technology to solve wireless optimization problems, and that will lead us to some advantages over the classical approaches. So just to briefly go through my background, I'm in Germany in a city called Bremen. It's Construct University. He mentioned that it used to be called Jacobs or Jacobs University in German. And I'm under Professor Giuseppe Abreu. So I first want to introduce my lab's general overview. So we do a lot of work, of course. I think every lab has many interest areas. And the biggest topic we do is integrated sensing communications already. We have done channel modeling, waveform design, and transceiver design, so transmitter and also detection. We also have moved on to integrated communication and computing, so which is one of the topics called over-the-air computing. So we want to combine these two ideas as well. We also do a lot of wireless localization, and we are looking into what's called a rigid body localization as well. This is not a point-based localization, but we assume that some body has many points, and these points, we know the conformation, which is the structure of this body. So like a car would have some corners, and this information is accounted for in the localization algorithm. And of course, we also do some machine learning based as well. And then we look into some next generation reconfigurable metasurfaces, so looking beyond the RIS or RIS, and we look at beyond diagonal RIS, stacked intelligent metasurfaces. This is continuous aperture phased array, so this is a continuous version of RIS, kind of, or MIMO arrays, and also this dynamic scattering array. And then, of course, some physical layer security and also quantum computing-aided wireless systems. And today, out of many of these topics, I will talk about these three in three parts. So again, over-the-air computing, waveform design for ISAC, especially the AFDM, and then the quantum computing-aided wireless system. So the first part, over-the-air computing, I'll briefly go through the fundamentals in case you're not familiar, and then present two of the works that we are doing, which is building on top of the conventional over-the-air computing framework. So over-the-air computing is also called over-the-air signal processing or wave domain computation. Also, its acronym, there's AirComp, OTAC, OAC, OTA, but I think I use both AirComp and OTAC for my presentation and my papers. And this basically deals with a scenario, a very specific scenario where we have many number of users. And for the example, we have K number of users, which are all equipped with single antennas and a single base station or access point, that is a MIMO, a multiple antennas receiver. And we assume that each user has some data, D of K at the user. This is a real value scalar. So this is some like maybe a temperature measurement or some measurement that it makes, or even some information data. And the objective is to compute some function of the user data and not the individual one. So we don't care what the individual data DKs are, but we're interested only in the multivariate function. So some examples that we want to compute, for example, could be the summation, so product, average, maximum, and so on. And these are, as you can see, some multivariate function that is relevant for the user, especially in IoT scenarios, for example, or vehicular communications. So the most straightforward approach that you might think that is easiest, actually, of course, is first modulate the symbols, so encode it into some complex or even real symbols, and then transmit using simple any modulation technique or waveform. Then we first estimate the individual data as the d tilde, individual data, and then we compute this multivariate function. Of course, this is nothing new. This is classical wireless communications and using the function. And what we want to do with over-the-air computing is make these last two steps at the receiver more efficient and more energy and more computationally efficient. And this is important for massive IoT where we want to have low energy, or also critical mission cases where we want to have much lower latency. So we don't want to spend all the time decoding all the information and then computing. So to enable this efficiency in the last two steps, we have to use something called a nomographic function. A nomographic function is a multivariate function, a real multivariate function. So it takes in R of k, so k number of real values, and then returns a single real value scalar. And the important characteristic about this nomographic function is that this function can be decomposed as a post-processed sum of pre-processed data. So if you can see on the right side, this is some real valued raw data, so d of k, this is the original data. And we have some pre-processing function, phi of k. This is different per user, so we have different pre-processing function. And then we sum this pre-processed symbol. And then this is, again, this total sum is, again, post-processed. And if any function can be formed into this decomposed form, we call this a nomographic function. And how this is relevant, you will see. So first, if we take the simple pre and post, both of them to be just identity functions, so it does nothing. If you put it into the original form, we have this pre-processing function is identity, so it's just the data. And then we also have nothing in the post-processing. This results in a simple summation, right? That's clear, and that's not very useful. But if you now take a logarithmic function for the pre-processing and exponentiation for the post-processing, so any base actually, this formula results in a product, right? So this type of functions can be useful, and actually most of relevant or general wireless communication functions that we want to compute in these scenarios can be written into nomographic forms. So you can see summation, multiplication, geometric mean, harmonic mean, maximum. So this is both maximum or minimum. And this softmax means that we can actually tune the softness of the maximum by having a value beta. So large beta means it's more a strict max, and then value close to 0, it's more softmax. Any polynomial function, that's approximation, and many other functions that we can do. And in the worst case, even if they cannot be directly put into this nomographic form, you can approximate any function using a sum of many nomographic functions. So that is just the fundamental of nomographic functions and why this is useful. So what's the point? Now we go back to the original scenario. I have many users with their own data. The idea is to let the wireless channel, which has, of course, we know that wireless superposition, all the signals are summed already at the receiver automatically, of course, assuming that they're synced. Then, if we encode the data not using a classical modulation constellation, but using this pre-processing function, this will be summed at the receiver. Of course, there will be some complex coefficient with the channel, but the summation is done already by the superposition effect. So then at the AP, we have multiple antennas. So we have this received vector, y1 to yn. Each of them is the sum of the individual user pre-processed data multiplied with the channel between that antenna and the user. And the goal is to, now we have this already automatic sum done already. We want to apply a single combiner vector. So not processing estimating the exact data, but only applying a simple combiner vector. So this combiner vector called U, applying this vector to yield some estimate of the original sum, that has already taken removed the effects of the channel. So it's kind of like an equalization, but over the sum already. So we don't equalize the individual data. So the goal is then to have this single vector. Then we no longer have matrix inversion, matrix multiplication, solving the linear problem. It's a simple vector. So it's a vector multiplication, so it's very efficient. And that will directly give us some scalar, that is this direct sum. And then we can just apply the post-processing function directly to get our estimate of the multivariate function that we are interested in. So this f of tilde, this is the estimated function, and that is simply getting the received signal, applying the combiner, then a single scalar function. So it's very efficient. So comparing, now going back to the classical method that I mentioned in the beginning of this section, this part, we first have to encode the data into some modulation symbols, solve this linear equation for the x, and then demodulate or decode the individual data, then compute the function. For the air comp or over-the-air computing, the modulation is equivalent to the pre-processing, this single function for each user. And the receiver simply applies a vector and that's it. So you can see it's very efficient. And sometimes this post-processing function, depending on the function itself, so like we saw the sum already, it's nothing. So actually you don't have to even apply the post-processing. So it's a single vector multiplication. And based on this, of course, there's many problems. First is, of course, how can you actually make this combiner? This is simply normally done with some optimization, or what we normally do is just based on MMSE criterion. I won't go through all the details here, but we use that. There's also scenarios where we assume that there is some feedback between all the users and the AP. So then we can jointly optimize the precoder. So after the pre-processing, we can also apply some complex rotations, so precoding. So we can also do a much better estimation of the joint precoder combiner optimization. There's also another big line of work that can be done, and so on. So this, what I've just shown, is the conventional classical over-the-air computing. So what we've done is now try to put on top of this fundamental framework multifunctionality and better spectral efficiency. So this is a recent paper that I've published, I think, a few days coming to Korea, so last week maybe. So we call this the quadrature over computing for multimodal and dual stream signal processing. So what we try to do here is we go back to the idea saying homographic functions only work for real valued symbols. So we saw that this is transmitting a real valued symbol modulated with pre-processed with a real valued pre-processing function. But of course, we know that in wireless communications, we also have the full complex domain. So I thought, why waste this space? So as we went from the pulse amplitude modulation to quadrature amplitude modulation, or spatial modulation to quadrature spatial modulation, can we not put both data streams, one in the real part, one in the imaginary part, and then transmit them together? So now we have two independent data. So we called it DI and DQ. They're two separate, completely independent data. And at the receiver, we can apply two different combiners. One combiner to combine only the real part, one combiner to combine only the imaginary part. And then we get two streams. And these two streams can be performing because they're using different pre-processing functions. One could be doing a summation, one could be doing a product, or they could be doing the same function, but just twice the rate. So we have twice the data rate. So this entire framework is what we proposed in the paper. And just to show some preliminary result in the paper, it was only a conference version. First, we use both streams. So in this proposed one for the same function. So now we compare against the classical one, which is doing only summation in the real domain, and then the proposed one, which is doing two times the summation. So twice the data rate. And then we can see that we simply get twice the computing rate. It's not a capacity because we're also losing some SNR, but in terms of rate, or in terms of the number of data computed, it's just the twice. And then if we also see the CDF of the normalized mean squared error, we can see that our scheme, the proposed one in black, has a slightly better MSE performance than the conventional one, which is a single stream. And then if you also see here, this is also only for a single SNR. I think this was SNR 15, maybe. But we can see also the average SNR, average NMSE over the different SNRs also is consistently better than the conventional over-the-air computing scheme. And then I also mentioned that we can actually perform multiple functions as well. So this is actually the more interesting feature. especially because I'm with the vehicular technology team. Uh, they have a system where they put sensors on the tires themselves, and that is measuring, they said, typically the angular velocity and the tire pressure. And these are two simple, very scalar data. Normally, you would do two transmissions, and normally they just want the average or some function such that, for example, if the left tire is faster than the right tire, you can know slightly the approximate turning of the vehicle and so on. So this is one thing where we did was, in one stream, we did the weighted average, and the other stream, we did the arithmetic mean. And we can see that in this case, because both functions are kind of based on a sum, the average is simply a division of a sum. So they perform both perform well and about the same performance as well. And this is already not possible with the state of the art because you need to do two transmissions. On the right, we show two functions. One is a summation, one is a product. And you can see that the product actually loses some performance gain to the summation because when you do a product, as you saw, the pre and post processing function was an exponential and a logarithmic. So they're much more prone to small scalar errors in that case. So this type of error can be mitigated if you're, for example, using the joint precoder and the receiver combiner. All of this is just based on a very simple MMSE based combiner. Of course, then we want to get better performance out of every single function of this proposed scheme. And then finally, building on top of this, both the conventional and the quadrature one, we move on to what is called integrated communications and computing, so ICC. So we're familiar with ISAC, integrated sensing and communications. We want to do ICC, or even if you're being ambitious, ISCC, which is integrated sensing, communications, and computing. There are a few, I think, survey papers on this scheme. They try to motivate this, but I think there's no actual physical work yet, so we want to do this. And also, this ICC part is what we're contributing to this industry specification group of ISAC. And on this ICC, we also published a paper. This is a more bigger paper where so before this paper, to the best of our knowledge, there are many motivational works on ICC. They say, okay, this can be used for this can be used for that, but there was no concrete actual receiver design showing any results. So this is probably one of the first papers that do this. So we use message passing based algorithm detectors to perform this. And one very simple way we did was okay, let's have a symbol with high power communication signal and low power computing signal. This is like something like an RSMA type of overlaying of symbols. And of course, then we have different scenarios as well. We have homogeneous ICC where all the users are both sending communications and computing signals. We have multi-stream, which means it's similar to what I showed before, but this group of users transmitting computing one function, and this group of users transmitting another function. Of course, then the estimator has to compute two different values. We also have heterogeneous ICC, which is having some users don't transmit computing or communicate. They only do one, like we also have. And then some are doing both. So we also then have to take this into account, and we do a bunch of work in that paper, design the low complexity message passing estimator that improves against the classical matrix inversion based ones. And we show on the right that this is on 200 numbers of base station antennas, and then this number of users. Of course, so far what we found is that we cannot overload the antennas unless we have pre-coding. So this is just the combiner side optimization. So we can see that, of course, the state of the art is the matrix inversion based, the cubic based complexity algorithms. And our proposed one is a message passing based, which has a quadratic complexity. And it almost reaches the matched filter bound, which is the optimal performance. And we see that in both cases, both scenarios, we get a very good performance in both communications and computing in terms of the function normalized mean squared errors. And this was achieved only using, I showed that the power difference is quite large between the two. In this case, with the computing signal only had 1% of the total power, and it was already getting good performance because we can also then perform interference cancellation. Then we do the computing signal. So that was what was actually done here. So we showed that even with very small power, just added to the communication signal, which is almost like noise in that perspective. So that, I think, is the first part of the presentation. I'm not sure if you should take questions in between or at the end, but maybe at the end, because I also have a summary slide. I think that's better. So then we can move on.